Okay, welcome back. We have another session on information processing, actually, and climate change. These are two slightly different papers, one a little bit more formal here, or more in the sense of the ambiguity. And then Min has probably a little bit more of applied thoughts about the problem. And then Rick will discuss it afterwards. Andreas, please start.
Okay, yes, thank you for having me here. It's great to be in Berkeley once again. And what I want to talk about now is basically to bring together two different things which have been discussed in the last couple of, or 2 days. One, we had a couple of sessions about different decision criteria. So non-expected utility maximization, Paolo was presenting different ways of how to deal with ambiguity in a decision theoretic context. And on the other hand, we had this more applied studies basically dealing with climate risk and how we really can deal with uncertainties in different sort of models and what might be the impact of climate change in the real world. So now when you try to bring these two things together, it's basically the question, okay, given that we have those climate risks and a certain decision criterion, now what does it actually mean for our decisions? So how does, for example, uncertainty actually affect our decisions? And that's one thing in a very stylized way, in a very simple way, which I want to talk about here today. And the models which I will be using are completely simple and, of course, not intended to even reflect a tiny bit of the reality. So that's a caveat which I have to give you here in the beginning. So, I mean, we've discussed about all those things already. So we have climate policy, we face lots of uncertainties. Of course, there's also the chance that we'll learn a little bit more in the future, so that learning can take different forms. And I think in the next talk, we will hear a little bit more about different ways of how learning actually can occur. And of course, also we talked a little bit about, or talked a lot about ambiguities and uncertainties. That just if you look into the IPCC reports, I mean, they have basically different ways of how to describe uncertainties. If it's just based on the models, is it basically based on just not knowing specific values, or is it some more essential uncertainty that we actually have no idea, and we cannot even learn because we will always be in a range where something unexpected can actually happen. So now, this motivation was given before, so we have a situation where not necessarily, or we cannot really apply objective probabilities, but now the question is, okay, do actually people, when we put them into the context of making decisions on climate policy, do they actually behave as if they are expected utility maximizers, or do they behave in a different ways and, for example, use Choquet expected utility maximization or the KMM idea, etc. And of course, there are different theoretical approaches which one can use in order to describe the behavior of people. Christian was talking a little bit yesterday about the question, should we actually even think about applying those sort of models to a normative world, right? Basically, should we now really consider these sort of models in order really to advise policymakers in terms of what kind of decisions they should do? In my talk, I will just take the standpoint, okay, let's use a certain decision criterion and just see what the decisions would be. Right, so you can think about this as your personal, or maybe the personal desire of different people to invest into climate policy, and then that might be aggregated in terms of voting or some other mechanism into the real policy world. Or it could be the policymakers themselves might have a specific sort of preferences and might want to deal with ambiguity in a certain way. So the presentation is structured as follows. I will first just describe a very standard way of how many economic theorists think about certainty versus uncertainty, or certainty versus risk, versus potential learning, and how that actually affects behavior. I will then talk a little bit about those issues in the context of a standard expected utility maximization. And then in the end, basically, we'll apply a specific form of non-expected utility models, namely the KMM model, in order to say a little bit about how that decision actually might change if people might be ambiguity averse or potentially even ambiguity loving, as we have heard before. Okay, that's a simple model, and this is how I think about climate policy and climate change. So just assume we only have 2 periods. So we can basically decide today what we want to do, how much we want to invest into some abatement options. So that's the decision in period 1, x1. And of course, there will be some future time, say in a decade or 20 years or something like that. We also have to decide on a level, and at that moment in time, we potentially have some better information about some sort of underlying parameters. And the uncertainty is captured in that model in a very stylized way. We just have one parameter which basically captures uncertainty. The theta is not known in advance. And we now can basically discuss different cases. And one standard case is, okay, what about if there's no learning? So we just have certain beliefs today. What would we decide? Now, what about the case in which we basically have perfect learning? That basically means that even before we make the decision in period 2, we get some new information, and that information perfectly reveals the state of the world. Of course, that's completely unrealistic, but as an extreme scenario, maybe worthwhile looking at. And the third case, which I only will touch, and I think in the next presentation we will hear a little bit more about this partial learning scenario, I believe, I'm not sure, but would be basically where, yes, we get some new information, but still we are not really sure about what will the theta in the end really be. So basically the structure, we make some decision today, x1, we might or might not get some new information before we have to make the decision in the next period, and then in the end, the theta, so that uncertainty basically realizes, and we have a specific utility or payoff or however you want to call that. Now, 2 very simple models which have been discussed in the economic literatures are the following. Model 1, cake eating model. So basically in each period we just eat some part of the atmosphere or just some part of a cake. x1, x2, the problem is we don't really know how big the cake is in the end. Right? So the theta basically is just the size of the cake. We can basically take 1 share in period 1, 1 share in period 2, and in the end we just have to eat whatever is left over. The other model has been discussed in a couple of papers, for example by Alistair Alf, where they basically tried to incorporate a specific feature of the climate policy problem where they say, okay, now we can basically emit something today, and maybe if we reduce our emissions today, we have to bear some abatement costs. So, but basically the utility today depends on our decision today. We might also have a second period where we also can emit something or abate, however you want to call that. But in the end, we basically will face some damages from climate change. And the problem is clearly that the damages from climate change do not just depend on the emissions in one particular period, but on the stock of the emissions. Now, if you only have 2 periods, it's clear that the damages must depend on the sum of them. I completely ignore any possibility that the stock actually will go down in that time period which I consider here. And as you see, I also completely ignore any discounting which Christian was talking about before. But I mean, that's just one extreme scenario. So now, the way people quite often think about risk and how it actually affects decisions is the following. Basically, to say, yeah, we are not really sure what the theta is, so we only look at the expected utility, and we try to maximize this. And now it's an extreme scenario. We can just say, okay, what would we actually do if we knew the parameter theta with certainty and just look at the expected value of it? So I had this discussion with Klaus just in a break where he said, okay, there's some discussion of how people actually deal with different predictions in the IPCC report. And one thing, for example, was when you think about coastal defense measures, now they say, okay, how high shall we actually build our dikes? Okay, let's just take the mean of the sea level rise and just build the dikes according to that thing. So now the question is, does it actually make sense? Should we do more or should we do less? Right? Probably everybody would say, no, just taking the mean doesn't really make sense, right? But in what kind of directions should we actually adjust this level? And that's actually something which one can first look just at this very, very simple framework. So now, The problem, of course, with all those theories is it completely depends on how the uncertainty enters the model. So now if it's building dikes, it's completely different from even those two settings which I describe here. Now, if we have this cake-eating model, our example 1, model 1, now here basically it basically only depends on what is the third derivative of our utility function. Are we prudent or not? If yes, okay, then even under uncertainty, we would basically eat a little bit less of the cake today. If, however, the third derivative is negative, it just goes the other way around. Yeah.
Where exactly is the risk coming in here?
I mean, here it's just we don't know about the theta in advance, right? I mean, we basically here it's just this a case where we just say let's assume that we knew about the theta and just put in the mean, and then just optimize. Or here basically, how do we account for our uncertainty or the risk? And now you basically can easily see that that enters this model in a nonlinear way, and for that reason, basically, it really depends on the third derivative. Now, in this model 2, however, it's different. Here, the uncertainty in that very simple model enters in a linear fashion, and for that reason, basically, uncertainty here doesn't have any effect on the choice. So if this is really the way how we can just think about uncertainties in any model, you can just say, okay, let's just use the mean of the parameter, which we have no idea about in the moment, but just use the mean and just plug this in the model, and at least we get a decent guideline for how behavior might even look, even if there's uncertainty. And now one basically can adjust this a little bit to the higher, lower, depending on how the structure of the model actually looks. But the problem clearly is that there's no definite answer. We really always have to study how does the uncertainty really enter the model, how does the uncertainty really enter the specific structure which we think about. And only then we can make a conclusion about how uncertainty and the certainty case actually differ in terms of the decision. So now the next thing is, what about learning? What about the case of perfect learning in the extreme? So now perfect learning basically means before we make decisions in the second period, we will know exactly what the theta is. Right? So basically we can condition our second period choice on the realization of this uncertain parameter. Now what that basically means is there is something missing. That's basically the derivative of the utility with respect to the second element. So we just choose the optimal x2, the optimal decision in the second period. And in the first period, we clearly have to take this into account. And now it's very easy to see here when you just say, okay, now how does this differ from the effect under uncertainty? Now it just matters if this whole function here is concave or convex in the theta. So basically, according to Jensen's inequality, can we put the expected or expectation operator inside the brackets or not? Right? And that's, again, depends on the structure of the problem. Again, we have a similar thing here for our cake-eating example, where basically perfect learning now would, or the possibility that we actually will learn before we make the second period decision now allows us to eat more of the cake today. Right? So there we have, if we are prudent, we basically had the situation from certainty to uncertainty. It basically means we eat less. But now, since we know that we can actually learn something, we can again eat more in the first period. So now, in the other example, where we had seen that because of the linearity, it was not at all of importance what uncertain or how uncertain actually that parameter is, right? Basically, because of the linearity, only the expected value of the theta mattered anyway, but now that's different in case of learning, because now here, this function can be concave or convex. We don't really know in advance. For a specific case, for say quadratic utility, which is quite often really easy to handle in these models, and that's why people quite often use this, we get the result that yes, we can eat more today because we can learn. So which basically would mean that the possibility of learning in the future can lead us to emit more today. right? So that's now maybe something which one might not anticipate, right? If people think about this in the terms of a reversibility effect, and one always should maybe do a little bit less because we have the possibility of to learn something in the future. But that's something different here because there are two different sorts of irreversibilities. One is that we build up the stock of greenhouse gases in the atmosphere, so we cannot just get rid of that unless we basically invest into geoengineering or something like that, right? But there's the other irreversibility, which basically just means that if we do abate today, we just have to commit to certain abatement costs. We also cannot recover those. And those two sorts of irreversibilities, it's not really clear in which direction they will play out. It could go up, it could go down. We're not really sure about this. Partial learning is another case. Since we have no unambiguous result for perfect learning, it's clear that we cannot expect anything simpler for the case of partial learning, and that's why I just forget about this here. Just in terms of behavioral models, since I'm also doing experimental behavioral economics, of course, there could be other motivations which come into play. Right now, all of a sudden, a partial learning case could, for example, lead to a setting where I just get some misleading information. Right? So I do something, then I basically say, oh, climate change doesn't really occur, that was not that severe. Right? Then I say, wow, I can really pump something into the atmosphere the second period. But in the end, say the worst case occurs, and now I might suffer from regret, right? And just, I should have ignored that information. And all of a sudden, basically, in terms of behavioral models, many other motivations come into play, and they might actually change the behavior of people. And that's not necessarily captured by any of the models which we have discussed so far in this workshop. So that's basically one way one can also probably adjust many models on climate change if one introduces some ideas of regret or disappointment. Now, what about alternatives to expected utility? We've heard about a couple of approaches: Choquet expected utility, just multiple priors, the KMM model, which was discussed extensively yesterday, which basically has this nice feature of allowing for some smooth ambiguity aversion. And this is actually the one which I want to apply here. So we have this function phi, which basically just gives you the ambiguity attitude of the decision maker, of the person who chooses x1 and x2. And what it basically does is we have some sort of probability distribution, but we are not exactly sure about those. We can put in the expected utility, but then again, we have a certain weight which we attach to each individual probability distribution. And now the question is, how does this ambiguity attitude actually change the decision in our two cases, our two models? Now, here the important point clearly is that if people are ambiguity averse, it basically does the following. It gives a larger weight to the probability distributions which have a low expected utility. But now the question is, what does it mean for decisions? So now, out of a sudden, we have to ask the question, is a low expected utility actually associated with a lower marginal expected utility, yes or not? If that's true, basically a low expected utility and those events are evaluated or are given a larger weight, and that goes along with a low marginal expected utility. Now probably then we would emit less today. If, however, it's the other way around, we can emit more. So it really depends on how expected utility and expected marginal utility are correlated. And that's something which quite often when you only look at the decision theoretic models and some axiomatic approaches, one doesn't really consider that. And it's really important always to say, okay, in a specific case, just like in expected utility maximization, is the low utility associated with a low marginal utility, yes or not? Here is a low expected utility associated with a small marginal expected utility. And of course, again, the models can give different answers. Again, we can go through all the different cases, certainty, uncertainty, and perfect learning. And just look at the uncertainty case now here. Just as I said before, the weight of a specific probability distribution now out of a sudden depends on this phi, or the marginal value here. And then the question is here, what is the marginal utility? In the example 1, or no, example 2, that's a climate model, right? It's clear that the smaller expected utility is associated with a smaller marginal expected utility. Basically, if the damages are enormous, so really climate sensitivity is extremely large, and in the end, we are in a scenario where basically we have severe climate damages. Because of that multiplicity, how the uncertainty parameter theta entered the model, this large damages are associated with the large marginal damages, which basically means smaller expected utility is associated with smaller marginal expected utility, which basically says if decision makers are ambiguity averse, they should even further reduce emissions today. And that's some sort of a maybe intuitive statement. However, if one looks at the other scenario, if the other model, the effects are less clear. Just look at the quadratic case. That's basically where the decision maker is neither prudent nor imprudent, so basically where the third derivative is exactly equal to 0. And that's the case where under the expected utility framework, all the decisions coincide. It doesn't really matter if we have perfect learning, if we are uncertain, or if we have the certainty case, all the decisions would coincide. And that's why this scenario gives a nice extreme case to consider what's the effect of ambiguity aversion. Now here, as I said, if you're ambiguity neutral, you're just expected utility maximizer. There's no difference between uncertainty and certainty, and also no difference between perfect learning and just a certainty scenario. Now here is it, however, if people are ambiguity averse, the qualitative effects again depend on how the variance and the mean are correlated. And of course, one can describe different probability distributions. Right? A large mean could be associated with a small variance or the other way around. So even so, in this particular model, under expected utility maximization, we had this nice feature for the quadratic case at least, that decisions really don't depend on if we consider learning or not, or the other scenarios. Now here, under ambiguity aversion, it again can go either way. We are not sure. It really depends on how the distributions look like. And we do not just have to consider the mean. We do not just have to consider the variance, but we always have to consider both and have to answer the question, is a small mean associated with a small variance or the other way around? If we have a statement there, then we actually can derive some unambiguous results in this cake-eating scenario. And similar things actually now occur for the case of perfect learning, that here, even for quadratic utility function, one basically obtains ambiguous results. So it's not really clear what's going on. So I think to put this a little bit into the context, again, risk aversion just puts a larger weight on low utility events. Ambiguity aversion puts a larger weight on low expected utility distributions. And in both cases, the qualitative effects are quite often very similar if you look at many of those decision frameworks. However, of course, what I didn't consider here are any really dynamic extensions and some updating, right? Because if you only consider perfect learning, it's clear what's going on in the second period. If you don't consider perfect learning but have some partial learning, you have to think about what is the dynamic extension of the model. And here, of course, it now depends on do we have the recursive structure like in the KMA model, or do we look at Choquet expected utility maximization, look at some behavioral consistent choices, or just give up the consequentialist nature of our decision criterion. As a conclusion, it is important not just to look at how large damages are, but also how, when damages are large, what can we actually do about them? Right. So basically, it's just a call for if we want to assess climate change or climate damages, then basically one should not just say, okay, under this situation we have to expect this particular damages, but in order to give a decent foundation of any decision, one needs to put this into context with, if the damages are small or high, what are the marginal benefits from abating today? And only if we have those two information, or those two levels of information, we can actually really put them into some cost-benefit analysis framework. If not, we're sort of lost. It doesn't really help us as economists just to see some climate models and say, okay, now that's the damages which occur, but basically one really needs to assess different scenarios. And then the question is, and that's something which clearly as an economist one usually cannot answer, is, of course, if you look at IPCC reports, you have different scenarios which are calculated. Okay, and under scenario 1, we have to expect those sort of damages. Under scenario 2, we have to expect this other sort of damages. But now the question, can we just put them into a linear framework? I'm not exactly sure. There are so many uncertainties and so many different variables which differ in those different scenarios. But for the marginal damages or marginal return from our abatement efforts, we really need some information about what's happening in between. So what does actually, how does 1 unit of avoided emission change the future climate scenario? And that's something which is probably really hard to obtain, but it's really necessary in all these models. Okay, that's, I think, all I want to say.
Thank you, Andreas. Yeah.
All right. Thank you. So I'm going to talk about another kind of learning, which is hopefully more realistic, because I tried to pick my ideas in the sociology of science. So it's about decision making in a situation when you have many experts and the experts don't agree. So how do you aggregate the opinion of experts? So basically, it's a problem of how to aggregate experts. And I will frame this in a variant of the Dempster-Schaeffer model. So it's called the transferable belief model, but you can think a bit about it as just as Dempster-Schaeffer. And then I will explain my aggregation procedure. And as you know, in ambiguity analysis, we make a very clear analytical difference between equiprobability and no information. So in the Dempster-Schaeffer model, you have a void beliefs that represent the state of no information. But what the transferable belief model adds is that it represents the state of a contradiction, which is very convenient because when you have experts that disagree with each other, then of course you want to use a theory that is para-consistent. And para-consistent means that the theory can deal with contradiction. And the way the transferable belief model does that is that it assimilates contradiction to unknown unknowns. So I think it's not the strongest point in the theory. So actually, it's a weak point to say that incompleteness and contradiction is the same thing, because unknowns are not the same as contradictions. But anyway, and so I'll have to talk about negative information. So you have to remember the first time you were introduced to negative numbers, or the first time you were introduced to complex numbers in physics, because if you'll have to admit negative information. So the idea is that you use negative information in the computations, but it disappears in the end, of course. OK, so I'm going to talk about climate sensitivity. So everybody knows that it's a long-term global warming if the CO2 concentration in the atmosphere doubles. But there's another aspect to this value. That's a social science aspect. Is that climate sensitivity is a communication anchor. So it's a way for the science community to say to the policy community how dangerous is climate change. So it has a uncertainty range, which has been for a long period, 1.5 to 4.5 degree. And only changing this range could only be justified if there was a new science that make it very clear that it's more dangerous. So it's a very uncertain communication anchor. And in 1995, we did not have all these PDF simulations that we have today. So the way to have information about it was to get subjective probability distributions from experts. And this is just what Granger Morgan and David Keefe did. And so they asked 16 climate scientists to provide continuous probability distributions for climate sensitivity. But in what follows, I have divided the range into discrete intervals. So you can see that some experts had a very broad probability distributions that allowed some non-zero probability to -6 climate sensitivity or to plus 12 degrees climate sensitivity. But of course, very small with a very small probability. And well, here are what the 7 experts, what the 16 experts gave. So each cell in this table, it's 1 expert. And the histograms, they represent the probability distributions. So the sum of the area in each histogram is the unit mass. And I will use that unit mass later. And now we can group the experts into 4 clusters. So the first cluster with experts 2 or 3, for example, they give a positive probability to every state of the world. So they say that everything is possible, basically. Now, experts like expert number 4, they say that cooling is not possible because there are very good thermodynamic reasons. But they do not exclude very dangerous climate sensitivity. And then you have experts like expert number 5, who basically they take the IPCC official range, 1.5 to 4.5, and they allow a few small tails around that, but not to the negative and not above 6. And then we have the outlier, who is in denial. And this outlier says that climate sensitivity is between 0 and 1. And this makes the aggregation problem interesting because this outlier is as qualified as any other. So why is the problem interesting? So many reasons. First, for experts, they cannot be viewed as independent sources of information. So you don't really want to add their opinions carelessly, because you would have lots of accuracy, but based on the same data. So you would be double or triple or multiple accounting for the same evidence. And of course, you have expert number 5 who brings contradiction. So you need a para-consistency. Then the way out is to average. So classically, expert aggregation is often averaging. But then sociology of science and philosophy of science says that scientific validity is not the same as popularity. So really, I don't want any kind of averaging or majority. I want to give minority views an equal attention. So another way of would be to calibrate the experts and to say that some experts are less experts than others. But then first I can't do that because I don't have the name of the experts. And then it would be well, I have the name of the experts, but I don't have numbers. And you can't calibrate some things where it's a unique experiment. So what I do is I'll do what is a hierarchical fusion procedure. So first, the experts are clustered or partitioned into a school of thought or series or groups. And within each group, I do the cautious combination. So I don't assume that they are independent. And between groups, so we assume that at least one theory would be the good or the right theory, but we don't know which one. OK, so enough for the philosophy. Now the mathematics. So as I said, beliefs they can be represented by allocating a unit mass of beliefs among the states of the world. So at the top, you see, I think, expert number 1. So it's a probability distribution histogram here. And below, it's a mass function that corresponds to this probability distribution. OK, there are many ways to make a correspondence between a probability distribution and mass functions. But this one is simple and has theoretical grounds with a maximum entropy principle, a kind of maximum entropy principle. So basically, so you just cut horizontally the mass function instead of vertically. So you have beliefs, for example, that the state of the world is in omega 2, omega 3, but that is not specific. And here's another kind of mass function. It's that will be called a categorical belief. If you believe that just the state of the world is in a subset with full infinite confidence. So that will be called a categorical belief, and it will be denoted with infinite superscript. And of course, the point is that I will use over superscript to denote beliefs where that the state of the world is in this subset, but with less than perfect confidence. But before that, I'll show you two special kind of categorical beliefs, the empty beliefs. So if you don't have any information, you don't know anything. So that's the multiple priors that has every possibility distributions, if you want, or the void beliefs. And then that's the difference in the transferable belief model compared to Dempster-Schaffer, is that in the transferable belief model, you can allocate belief mass to the empty set. In this case, you would have you would represent the case of too much contradictory information. So One case is when you have no information at all. The other case is when you have too much information. And I say that this could be used to represent an unknown because the empty set is the state of the world that is not described by any other event in the frame of reference. But that's not the way we use it here. OK. So now, state of the world. The state of the world is something with a degree of confidence. So if you take from categorical beliefs that you say, OK, the experts tells me that climate sensitivity is between 1.5 and 4.5. But really, I don't believe that the expert is completely certain or is completely right. Maybe I misunderstood or whatever. So I will dilute the message with empty belief. So I consider this the belief function to the right by diluting, and I call this a simple belief. Or, well, Schaeffer calls this a simple belief function. And OK, and this is a simple belief function. So if the degree of confidence is infinity, of course, you don't add any doubt. And you just have categorical belief. And if you have zero confidence, then you have void beliefs. And this is where I change the point of view on this notation. So instead of seeing this as a state of belief, I will see this as a state message. So it's a change of belief. So it's a message. So the expert tells me the state of the world is E, and I take it with degree of confidence S. And I allow negative confidence. So if I think the expert is trying to mislead me, I will allow for negative degree of confidence. So I allow for beliefs with S negative. OK, now the operators of the transferable belief. So the first is the conjunction operator. So the idea is that when you have two fully reliable information sources, well, you just, one says something, the other says another thing. You believe in the intersection of what they say, because you just believe you believe them both. And the way to generalize this idea to non-categorical belief functions is to use the Dempster's rule without normalization, which is mathematically defined here, with the idea that if they contradict, then everything here will be 0, except for the empty subset, where it will be 1. And then you have the converse operator. If you have two information sources, but you know that at least one is reliable, then you would consider the union of their opinion. So anything that they say is correct. So instead of having an intersection, you take a union on this operator. And here's what was not known in a Schaeffer book, is that if you allow for negative degree of confidence in the simple beliefs, then you can decompose any belief functions that has non-zero mass to the frame of reference as a product of simple belief functions. So basically, you can say that any beliefs is a product of elementary messages, but focused on a subset. But some messages are positive and some messages are negative. And why is that interesting to do? That's because then when you do the conjunction, it's just like you are adding the weights of evidence, which allows to see very well that the conjunction, it increases the confidence. So if you have two sources of information that say the same thing, so consider you are a journalist, so someone, you have one information sources give you an information, a lead, then you have to confirm with another information source, and then the weight of confidence has increased. And this is what you should do. You should always seek independent information sources. But when you have experts, that's not what you have at hand. So you should not. It's not a very suitable, good operator. So instead, what Thierry Donner suggested is when you have two experts, instead of adding the weights of evidence, you take the maximum of the weight of evidence. And now this is where it's not obvious mathematically, because you have to demonstrate that in the end you don't find you find belief functions, because you so the idea is that you follow the most confident expert. You don't just add them. And there's an interesting consequence of the fact that this cautious combination operator is distributive compared to the combination operator. Is that if the first belief, if you are interviewing two experts, but the experts, they share one source of evidence. So for example, one expert, he has looked at paleoclimatic data on the tree rings. And the other expert, he has looked at a model on the tree rings. Then if you do the cautious combination of experts, then you count the evidence M3. Oh, there is a mistake. You count the evidence only once. So you are not doing double counting. So that's what you want for experts. So how does this apply to the fusion? First, I'll come back to the challenges of information fusion. But as I said, you have to have a para-consistency. And averaging is a way to deal with outliers, because you give them a smaller relative weight. It works also if you consider the union of opinions. And it doesn't work if you consider the intersection of opinions, because the outliers will give you only the contradiction. Then the problem of independence and interactivity, which is solved by averaging. But it is solved by the cautious combination, as I just have shown, but not by the other two. And then the problem that science is not a democracy. So you cannot really use averaging and pretend to have a sociology of science grounded fusion operation. And I don't want to add too much doubt to my experts, because I don't have any empirical way to do that. So basically, it says that there is no fusion operator that can do the fusion, so we have to resort to the hierarchical fusion, as I said. So first, cluster the experts. Then within each group, so the experts, you should assume that they have looked at the same data, and they have discussed together, but co-published, maybe, or studied under each other. So we use a cautious combination. And between each groups, so I cannot know today which theory will be right in the end. So I have to use a disjunction. So mathematically, I do just this operation. using the groups I explained in the first slide. Now, before I present the results, I have to do a bit more about the transferable belief model, because belief function, or a basic belief assignment, or a mass function, it spreads a unit mass of belief among the subsets. So you can have 2 to the power of omega, so that's 2 to the power 7 numbers. So it's not convenient to represent. So instead, we'll represent a probability that is associated with multiple priors. So yesterday, that's a probability that is in the center of the multiple priors, in the set of multiple priors. And you can also look at a plausibility function. It is more on the top of the set. And here's the result. It says that I will first look at the table. So here I have, as I said, the experts, they gave result on -6 to +12, but I made a discretization. And what's interesting to see is that because of expert number 5, it's completely plausible that the climate sensitivity is not very high. So at that time, we could not exclude the fact, based on this survey, that there was not a very large danger. But also, the plausibility that it's above 4.5 degrees is quite high, 0.69. So you cannot exclude the fact that it is also a very dangerous problem. So what has changed since? Well, today, the belief that it's not dangerous, that it's less than 1.5 degree has decreased, actually. So what this empirical analysis shows is that today it's more serious. It's viewed as more serious. For example, in the last IPCC report, the scientists bumped a bit the lower bound of the range, and they qualified below 1.5 degree as very unlikely, so meaning less than 10%, whereas previously it was less than 100%. And Kriegler also looked at the probability bounds and show the same thing, that nowadays the PDFs give a very low probability to a very low upper probability to this scenario. And how much time? 3 or 4 minutes. OK, well, just I have a sensitivity analysis to show you how much, to show you how the procedure, the hierarchical fusion here, but this is the picture I have shown already, compares to other procedures. For example, the first question is the sensitivity to the way of clustering the experts. So I made 4 groups. What if I made only 3 groups? Well, if I made only 3 groups, things would have been different. And the very high climate sensitivity assumption or hypothesis could have been much more, could have had a much lower plausibility level. So the method is indeed sensitive to a way of clustering. As I said here, so if you just average the experts, it works mathematically. My problem is that it doesn't work philosophically. Now, if you do the Dempster's rule. This rule is a way to combine the experts when you assume that there are independent information sources. So you have 16 information probability distributions, and they all converge around the official IPCC range. So if you combine them with this rule, well, you get back this official IPCC range. And also, it works mathematically if you are in a situation where you want to combine independent information sources. So as a conclusion, this approach, well, it fully deals with imprecision and ambiguity, which I think is a requisite when you are doing with expert opinion. And it deals with dependencies and contradiction. And I think, of course, there are ways to deal with dependency and contradiction in purely Bayesian setups. But maybe this one is more transparent, or I find it uses more linear operators than copulas or whatever. And it's more satisfying to me than averaging because it avoids majority rule calibration. And then it shows that the problem actually is a sociological study of the experts. So what you have to do to get robust results is to have a robust clustering. So I think this point is a bit overlooked in mathematical research and expert aggregation because we have sociological tools to group experts with face-to-face interviews. You can do economic cross-citation analysis. And this is very not often done. And of course, the climate conclusion is that above 4.5 degrees, it was already plausible in 95, and it's still plausible today. But below 1.5, it's much less plausible today than it was in 95. Thank you.
Asked to, does this work or not? Well, I hope this works. I was asked to comment a little bit on these two papers. I'm not sure, maybe it's better this way. To comment on these papers, and I'll also make some general comments. The first paper by Andreas Lange is about learning. So I'll try to give a bit of a view of what it's about and maybe have a few comments. Basically, in the paper, he talks about uncertainty and learning as it unfolds. So the uncertainty in his models would lead to a precaution, and that would lead to perhaps, as measured by a degree of prudence, to do with the third derivative of the utility function. And that mean that from an environmental point of view, you would take more action now. You have a more aggressive environmental policy. On the other end, he has something which he calls learning. I'm not sure whether I would call it learning, but basically you get new information coming in this two-period model, and then you adjust. You make the best of it. And then, of course, in his models, as time unfolds, you find out more. In a sense, it's maybe nice to wait a little bit, because if you wait, you might find out more, and therefore you kind of slow down your environmental policy. You do a less vigorous environmental policy, and these two things go in the opposite direction. So on the one hand, uncertainty would lead to a precautionary principle. Think a bit of the Stern report, if you want. And a more vigorous environmental policy, whereas learning would say, well, just hang on a bit, let's get a few more disasters, find out a little bit more, and then you would wait with imposing a very vigorous environmental policy. Now, I have a few comments about it. And the main thing I take away from the paper is that he's got two Mickey Mouse models with respect. So one is a two-period climate model, and the other one is what he calls a cake-eating model. I mean, you know, whatever they are, but they're very, you know, off-the-peg type models, you might have thought. But even those almost ridiculously simple models, so there's no offense to the author of these models, could lead to very radically different conclusions. So suggesting that if you don't quite know what the model is, you might, you know, you might end up with a more vigorous environmental policy or a more lax environmental policy. We can't even be sure a priori which model is more appropriate. So that already means that from a policymaker it's getting quite crazy because he doesn't know what to do, even in this simple little context. So now there are a number of comments. I mean, one thing is, of course, the model doesn't really allow for a multi-period setting where you have Bayesian updating or a Kalman filter or whatever. So it's really this one-shot information, and you just see what happens. So it really cries out to be kind of worked out in a more longer period context. More fundamentally, there is the question that there is no discussion of, it's mentioned, but there's no discussion of what we used to call active learning or of experimentation. So maybe we had a discussion on the first day, the football pitches of 200 by 200 meters, 100 by 100 meters, where people were trying to really have environmental shocks and then see what happens. Then I still think that type of learning, there's a bit of a problem there, which is the same problem with the Millennium Project of Jeff Sachs, where he tries to learn by scaling up all these little Millennium villages up and then trying to get an answer how it could be scaled up worldwide. And I think Jeff gets a bit over-enthusiastic there. And that same problem may be there if you try to learn with experiments, or if you try to learn in the real world, may be complicated. But it's an issue that needs to be addressed. On a more conceptual point of view, most of the models we've seen in the last 2 days have been what I call social planner models, or, you know, there's not much politics in it. So you could argue that in your models which you have maybe have multiple decision makers. So if you're in government and you're trying to do an environmental policy, then for a start, you have a problem that you have a weak portfolio. Because the Minister of Finance or the Minister of Economic Affairs or the Minister of Social Affairs will have more votes. And you're trying to push it through. And they will choose information which better suits their purpose. So I can give you zillions of examples of the Minister of Economic Affairs, you know, holding on one set of report, and then the Minister of the Environment another set of report. It is also beginning to relate to your paper. So there is a political economy of the use of information, which I think we need to address if you want to actually make sure that there is an interesting way of interacting with policymakers. But from a mathematical point of view, a theory point of view, we know, of course, from the work of, for example, Eric van Damme, from game theory, let me put it this way, that in such a gaming context, having extra information may actually be very bad. You may want to throw away information. Another Dutch guy, Peter Wakker, the psychologist, economist, or game theorist, has done this in a setting where I think you mentioned it, maybe also where there's dynamic inconsistency, then the same thing happens again. So information is a very different concept in a strategic setting. So on a political economy setting, I mentioned briefly yesterday, there's also the political economy of learning. So imagine that there's this idea that some people say there should be a policy ramp. So, you know, you have this kind of increasing hoteling kind of carbon taxes or carbon price of carbon permits, which goes up and up and up and up, versus the kind of the Stern type of approach, which is justified by I think Professor Heel has done things on that, Weitzman has done things, but whatever, where you have very vigorous environmental policy. But then you get, in a way, if you impose the precautionary principle, you must be pleasantly surprised. So it may become, there's more room for becoming a bit lax later on. That second way of approach, that has, from a political point of view, it begs the question what that might mean for a politician if you do it very environmentally. Then later on turns out the environment is not so bad. You're undermining your own case for a vigorous environmental policy. those type of political economy interactions, I think maybe we should look at them as well, I think. So that's not to say that this paper is not interesting. I think it's very interesting. There is a problem, like you mentioned the ambiguity aversion, where you used the models which Paolo and Susoy talked about. And there you see that what you get out depends very much on the particular model. So I think if you have the climate model, then the emissions in period 1 would go down. You would have a more vigorous environmental policy. Whereas in the cake eating model, if you had more ambiguity aversion, if I remember well, you might get that consumption in both periods goes up. And in a way, you will get a less vigorous environmental policy. So it's very interesting from an analytical point of view. But of course, from a policymaker, one, he doesn't understand what ambiguity aversion is. Secondly, if he does understand what ambiguity aversion is, and he says, well, what do I have to make of the fact, in the end, the policymaker just want to know, should I have a more ambitious environmental policy or a less ambitious environmental policy? So I like your examples, because they show that even in this very simple case, the results could go quite the other way around. Then coming to the second paper, before I start on that, I think that I should say that there's this old respected tradition of scenario planning. In Europe, it's often called the shell method. And basically, you construct scenarios. One is a wildly optimistic scenario and things like that, and then you sketch your life. Often you hire a literary giant in to kind of making a poetic description of what will happen in the next 50 years. And then you have a couple of other scenarios, a kind of a doomsday scenario, where you maybe get some artist in or some film to kind of really, and then policymakers can really start talking about it. Now what you're doing is, of course, I know the literature a bit from the past, that this Dempsey-Schaefer stuff. And I could say a lot about it, which I'm not going to do. But one thing I do want to say about it is that I think the idea that you have many opinions and that they may be incomplete, that the opinions will not be statistically independent, because often they use the same sources, as you pointed out. And there may be a contradiction among experts. Even stronger, I think experts sometimes deliberate, and I found doing it myself, if I go on telly, sometimes you really, afterwards, you say, oh, what an asshole I've been, but then you've kind of overdone your case in order to get attention. So you overtry, and if you don't overdo it, we got in Europe an example called Hans Werner Sinn. He overdoes his case always. Otherwise, nobody listens to him. And he says that, so I think it's a very human fallacy, which I know many academics will fall in that trap. So there is these experts that deliberately choose kind of contrarian opinions. Now, but what so I don't want to I like the way what you do, and maybe you do about it, but I do have some qualms. First, I would like to see more empirical work. And what I mean on that, empirical work on beliefs. So I've done in the past some work on immigration policy. And we know that people, they don't have proper beliefs, statistical beliefs on, say, if you just ask a simple question, how many migrants live in your neighborhood? People overestimate it by a factor 4 or 5. They say, like in Italy, Tito Buri has done that, for example. So now I wonder whether experts, so you want to know, could we find some empirical experts on how green or on what their policies are or whatever, or of decision makers, and what they believe? I think there may be a correlation there. In other areas, so I mentioned migration policy, people have done some work on these beliefs, which may not be, they may be subjective beliefs, they may be political beliefs, if you want, which I think would be interesting to incorporate in this context, and I think would be quite easy. So when you say, for example, that you think it's an advantage that you don't have majority opinion, I'm not sure. In the Bank of England, we have, in many monetary policy, banks have monetary policy committees. And the monetary policy committees consist of 7 or 12 or 11 people, not too many. They're elected every so many years, every 3 years, I think. And then they have discussions, which go on after they vote, they go public. And there's always a dissenting member. Now, the interesting thing is that there is no correlation between intelligence and being right. So we have, on the Monetary Policy Committee in Britain, We have perhaps the brightest economist in Britain of his generation is a guy called Tim Besley. Some of you might have heard. He's really quite a bright guy. And then we have somebody else who's a good friend, who's not seen to be quite in the same league. An applied labor economist, David Blanchflower. And he's never thought to be of this. He works actually in the States, and he's a good guy. But he was the only, and everybody thought, well, obviously, if I'm trying to kind of give weights a priori, so I of course give all the weight to Tim Besley and zero weight to all the others, because he's the smartest guy there. But that would have been very wrong, because the only person who had it right in the Monetary Policy Committee, when we're talking about this recent crisis, was actually Danny Blanchflower. He might have been right for the wrong reasons, but he was right. So this aggregation of views of experts and how you go about it and how you learn about it, I think it's a crucial issue. But I'm not sure whether the more slightly, the thing what you do is that you group people from the same school of thought together in different groups I like. But I think that this, again, this was slightly more, that there is this way of weighting it may require more than this slightly mechanical procedure you suggest, but that's something which is open for debate. I should come a bit to an end. I would like to make another point on, I've got to make a lot of points on learning more generally, which have not so much to do with these two papers, but I'll mention a few little ones. One, I think, Klaus has gone, but he told us about the RENT project. And one thing which I think is absolutely crucial, that most of the models we have, we give, thou shalt do that and that policy. That never works with decision makers. So what the nice thing was about the RENT procedure was maybe not theoretically the most interesting thing. He did everything upside down, didn't he? So you start with some policies, then you say, look, if you do those, these are the vulnerabilities, and then, well, if things go wrong, what can we do about it? And then you go back to the policies, and it's an interactive procedure between the decision maker and the experts, and where they both learn, the decision maker and the expert. So I would argue that learning is a crucial aspect there, is a kind of an open-ended procedure. So not this kind of top-down, say, you must do that. That's never how advice works. As soon as you do that, in an open-ended procedure, it allows you the possibility that you allow Obama to have his own aha moment, his own eureka moment, and say, look, I thought of this myself. And then they run much harder for it. So I think that element of learning is absolutely crucial, and maybe should be part of the second paper. Now a few more general comments about learning, and that's more to do about the whole conference. Then if I think of all the sources of uncertainty which have been mentioned, your paper was very enlightening, the first two papers on the conference as well, by John and Klaus. So just very quickly, we have uncertainty about the climate model. We have uncertainty about the climate parameter uncertainty. So the type of model, so like your paper, parameter uncertainty. We have uncertainty particularly about thresholds. Do we have thresholds? Where are they? When do they occur? Are they irreversible? Can we ever go back again? Do we go in a world which is a complete disaster or not? Usually not a complete disaster, it's just a different world which we don't know. And we call it a disaster, but it may not be a disaster. The nature of the positive feedback loops. I take away from these 2 days that we don't know much about the nature of the positive. We know that they're there. And maybe there may be more positive feedback loops than negative feedback loops, and that they can really amplify things a lot. That was John's point. But the exact nature of it he could not say. He said it may be there, but we don't know. We don't know anything about climate damages, not much. We know a little bit about it. I personally have a slightly different take on it. I think everybody is worried about delta T. I'm worried about the variance of delta T. So I'm much more worried about, if I look at your data or other data, you see this temperature going up and down in quite short, even within days or within years. And maybe there's a much bigger cost to the volatility of the temperature than the expected rise in the temperature. Now, almost none of the models we play with allow for that. Whereas for me, that would be quite important. There is uncertainty about the impact of climate mitigation policies. If I put on a carbon tax or a market for emission permits, I don't know exactly by how much CO2 reduction. We need to know that, but we don't. I need to know about the investment climate betas. We don't really know whether the correlations is positive or negative, and then how that would affect the interest rate. We need to know about the cost of climate mitigation policies, and we need to learn about it, but we don't know that either. Not much. We need to know then all the preferences of the decision maker. So if I've learned carefully to the theorists here, we need to know about the coefficient of relative risk aversion, the degree of intertemporal substitution, the degree of ambiguity inversion. We need to know how that all plays out into the social rate of discount you want to use. Quite a lot of uncertainty there as well. And one or two more and then I will stop, it's getting a bit boring. But we need to also know, maybe that's what somebody mentioned, initial conditions. But I don't know, for example, exactly what the total stock of fossil fuels we have in the world is. All I know is, okay, oil might run out in so many years, and then we still have 200 or 300 years left of coal. And coal is the biggest problem, but we don't really know. So there's a lot of uncertainty. Maybe that's what's called uncertainty of initial conditions. So there's all that stuff that needs out, and all of these things we need to learn about. But that's becoming a bit more pragmatic. So sorry, we went a bit out of hand there. Thank you.
Thank you. No, perfectly, thank you. And again, you will have time during the policy debate to go further into the details. For now, can the speakers come to the front, and then we might have some questions? And okay, we wait until the speakers are in the front. Fulvio, please.
Okay, I have a question for Andreas and one for Min. For Andreas, I would like to hear a bit more about the part that we have heard less, that is what you've called partial learning. Yes, partial learning. I agree that I don't like the word learning, but nevertheless. Now, you told us some results about that, but you, as far as I understood, you didn't tell us really how you model partial learning. Because as far as I understood, either theta shows up before x2 or shows up after x2. So, and there are the two cases, you know, the complete learning or not knowing nothing at all, and then showing up. So I was wondering how you can model partial learning in your setup, and I was worrying that the way you do it, you might mix up a bit things with ambiguity and learning, because either you, for instance, one way of modeling might be you receive a range of possible thetas, and you have to make an inference out of that, and or one other way might be you receive a signal and you know how ambiguous is this signal, so you might trust it or not. But then in that case, you are back with the problem that even when you deal with risk, actually you're introducing ambiguity in the model. So you don't really know then whether the result depends on the different risky setting, the two models you have, or the ambiguity of the fact that the signal you have received has been perceived in a different way. So I don't really know how you model this, and what you can comment about that. Perhaps the question to me I will ask afterwards then.
Okay, so this question of partial learning actually only addressed in the expected utility framework. And I mean, there it's relatively straightforward. You just get a signal, and that sort of changes your beliefs upon the distribution of thetas. And I mean, then you can basically try to deal with this in a certain way. A long time ago, my dissertation, I also tried to apply this climate model, this two-period model, to a situation in which people follow some Choquet expected utility maximization. And I mean, there I tried to deal with it in this sort of in the way of just looking at behavioral consistent decision path. So not using a recursive structure or anything, because this KMM model, which had this nice idea, wasn't out there at that time. And I mean, there it was also really interesting because, of course, like in this Peter Wacker stuff, you could also run into this sort of inconsistencies or even to some sort of negative value of learning. And in particular, again, I think the message of that paper here is just that the results, how the possibility of learning or even uncertainty can actually affect decisions, is crucially sensitive upon how you actually model the way uncertain or your uncertainty parameter actually enters the model. It can go either way, and I think that's the basic message. And if you apply that in this Choquet expected utility maximization framework, actually, I mean, it again looked like, yes, it can, or the possibility that even that you get a new signal, even if it's perfect or imperfect signal, can lead you to decrease your emissions today, or can lead you to increase your emissions today, depending on how the structure actually is. But it turned out that it could only increase your emissions today if actually the value of learning was negative. So basically, it's kind of, it was a really weird situation where one could relate this Peter Wacker story that the value of information might be negative to this story of actually how does the irreversibility effect play out? Should you decrease or increase your emissions? And there was a clear correlation between I only would decrease my emissions in a setting where I actually would ignore my emissions or where I would ignore my new information. So that was, I didn't now look at the partial learning case in the Klibanov model because that's more complicated.
Annie first, and then the second question of Fulvia.
So I have a question to Min on the aggregation of information from experts. So what I'm a bit worried about is your idea that if you have multiple experts telling you the same, then you assume that they're using the same data. What about scenarios in which actually these experts are using different data and they come up with the same idea in an independent way? So can you actually distinguish these scenarios at all? In which case, so if you were in this second scenario, then of course it doesn't make sense to group them, and it makes sense to consider that as even stronger evidence for the predictions that they're making. And the second question, I don't quite understand where the confidence into the experts comes in. Where does it come from? So is it some sort of an exogenous assessment that you have, or does it come from the predictions that they make? Can you, in some sense, compare the prediction of an expert to the crowd as a whole? And if he sticks with the crowd, then you're more confident, or so? I was wondering about these two.
If I had to combine the opinion of two experts that were based on different data that go in the same direction, I would use the combination operator that is appropriate for this case. So I would not use the cautious combination. So the answer is, I guess, no. My method doesn't account for this case.
Right, but so I understand that you want to make it conditional on the, but does your method actually incorporate information like that? Like what type of information the experts are basing their predictions on? How confident you would be? Do you have a way to incorporate that into your model, or the?
Well, expert elicitations exercise are actually not very mathematical. So the aggregation is not the most interesting part of expert elicitation. The most, because expert elicitation is made with face-to-face interviews with booklets, so directive interviews. So there are actually qualitative exercises where you the people who is doing the survey use non-mathematical methods, and the reports also non-mathematical findings. As for the confidence, well, I don't give any degree of confidence to the experts. So that's the point of this method, is that each expert is equivalent because each expert is within one group, and the groups are within groups. Experts are treated as equals, and the groups are treated also as equals.
Yes, the question is linked to the previous one. I have the feeling that at the end of the story of your paper, the crucial point is whether either you have some reason why you should group the experts somehow or somehow different way, according to your or the expert characteristics. So it's completely subjective the way you elicit the groups and the way you set the threshold of acceptability or not. And this is perfectly fine, I mean, but it's as fine as any other possible grouping or any other possible elicitation. So since I believe this is as fine as any other possible elicitation, why should we be so strict in this regarding the market selection of the expert, which is the majority voting that you were talking against in this discussion? Because either you have some reason of why you should know ex ante why some experts is better than others and why some have better information than others or not, or if you don't, then the majority vote is just simply the implementation of the principle of sufficient reasoning, the principle of indifference. That is, ex ante, you should believe that all experts can have can be as good as any other, so can have the same. Their report can be as good as any other, and then it's just the market that is if most of the experts have said something similar and some few have said something else. On average, they're better. So, I mean, it's a kind of, ex post ex post elicitation that is as acceptable as any other, unless you state clearly why you should have where are the information that you rely on that allow you to group them in a different way.
Okay, so why is this method better than just putting the experts in an IPCC room and asking them to produce a report? Putting the experts on a prediction market and asking them to trade? Well, this method, I think, is grounded on studies of how science works. And science works with in principle, the convention that all experts are equally experts, so everybody is a peer, and that you should not disqualify anybody. And if you don't use a procedure that gives equal attention to minority voices, then, like, for example, averaging, then it's certain that the media and the people will notice it and will point out that the procedure was used as unfair, and the procedure that gives unequal attention to the minority voices will be shut down when it arrives in the policy arena.
I would like to link this comment actually with one of Rick's, because I think it's extremely it would be extremely interesting to see that in a political economy context, right? I mean, basically, where now you said, okay, there's some model uncertainty, or maybe there's some different expert opinion, and now the question is, okay, how does the public actually deal with that, or different political parties? I mean, they might just pick the model which fits their purposes, etc. Right? So now the question is actually, what's the difference of if you use this sort of aggregation method for experts' opinion and then put it into the public arena, versus if you basically just have all the experts' opinion out there and then it's basically just gets aggregated in the political economy world, right? And I think that's some really interesting research which is probably still to do in that particular field.
Nick's comments were very interesting about the policy process and how there seemed to be comments about how the communication will really work and how that feeds into the decision. It reminds me, many years ago I had to advise the Deputy Under Secretary of the Treasury on oil import policy, and so I got my report done. I went down there and there were 2 people from Treasury and there were 4 people from EPA. And I was wondering why the 4 people from the EPA were there, and they were there because they had a number for what the oil price was going to be in 15 years, and all they cared about that my number was the same as their number, okay? So the one thing that they wanted to squelch was any idea that that number was uncertain, because that would sort of lead to confusion, and politicians are risk averse, so they just want to have one number, right? And about that time I went to a meeting that was chaired by a guy from Scallop Corporation, who was a corporation of Shell, and they had these scenarios and they'd actually been very successful at that time because they had forecast the first oil price rise, or at least had it among their scenarios. And the interesting thing was, it was incredibly simple and unscientific, but what they said was, it's very important to have a high and a low scenario, but what's really important is not to have a middle one. Because if you have the middle one, the politicians say, that's it, and they'll believe it's the absolute certain thing. And I think we have to think more about, the subtleties of communicating the really fundamental things to decision makers who think in simple ways and don't like to have uncertainty, not about the world, but uncertainty about whether people are certain about their policies, right? And I think there's a whole layer there that maybe we could do a lot more thinking about how can have even minimal communication of some of the really important uncertainties that they're facing.
I wanted to make, in a way, a criticism of your model framework, Andreas, but I have used the same model framework in looking at option value also. There's one way in which the 2 period is misleading. And you pointed out there are 2 irreversibilities. If you invest in abatement in period 1 and then it turns out not to be necessary, you wasted all that money. And if you didn't invest in abatement in period 1 and then everything, the world collapses, well, that was also not good. But in terms of time frames, they're very different. If we immediately started building solar power plants right now, and then 40 years from now or whatever, it turns out that there's geoengineering or the problem goes away. So we can go back to building coal-fired plants in 2040. I mean, we will have wasted money on solar plants, but we can. Whereas if if CO2 rises and the temperature rises 40 years from now, we're stuck for hundreds of years. So there are irreversibilities on both sides, but the sort of duration of the harmful consequences of the irreversibilities are different on the abatement side versus the damage. I mean, with 3 periods, that point can be made. But the point to emphasize is it is an artifact of 2 periods. That's all, because the harmful consequences of climate change last for irreversible over a longer period of time than the abatement cost. The second point I want to make relates to something that was said. In many cases, the disagreement in the real world is more profound than a parameter value or the uncertainty. It's about a model. I mean, for a long time, there was an argument, does secondhand smoke cause cancer? Or earlier, does smoking cause cancer? Yes or no. And there are arguments much more about causal pathways than the value of a parameter. I mean, you could say the smoking, well, the question is the parameter 0 or not? But as I say, the disagreements are often more profound because they're about pathways, not just parameter values. Now, obviously, if you, in a reduced form model, like a reduced form climate model, the climate sensitivity is the sufficient statistic. But often the model is not quite that reduced, so there's not just a single sufficient statistic. So the argument is, I mean, if we were doing it, we ought to try something where it's not theta, but there's a disagreement between 2 models, and you have to figure which is the right one. And there was a beautiful paper about halibut fisheries by an economist, I think at UBC, maybe I heard 20 years ago. And the story was this: there was a disagreement about the form, the shape of the stock recruitment relationship. So they're two alternative models. And each year, the fishery manager observes the recruitment, the sort of returning salmon, halibut or whatever, and the new population. And he has to make two decisions. He has to make a judgment which is the right model. So he updates the posterior probability. He starts off believing in one model, and then he gets data, and he does a Bayesian update, and then he decides, okay, given the new data, what are the posterior odds? And if the odds, go beyond 0.5 or whatever it is, if it go beyond the threshold, then you change believing in the model. And then the other thing is he sets a catch. So he has to manage the fishery. So each year he has to both manage the fishery, but revise his opinion as to the true model. And this paper then was a simulation. Suppose the person starts with the wrong model, just through bad luck, and marches through time, and there's a Monte Carlo simulation. How long does it take, how many years, before he discovers that actually this was the wrong model, and what happens to the fishery in the meanwhile? And in that simulation, it took 13 or 14 years, and by then the fishery was trashed. So it had been so overfished that it wouldn't recover. And I've always thought that was both an interesting problem and in a way maybe something to deal with. And you can see elements of climate change. If we believe in geoengineering, or if we believe some of the feedback loops aren't that big a deal, or are, we're partly in the middle. It's a bigger uncertainty than just the value of theta or the value of g.
Okay, I think the last point also, Klaus was talking about this yesterday, or I don't know, basically maybe it takes just too long in order to be able to differentiate between different models, and then it basically might be too late, right? I completely agree that this two-period framework or potentially three-period framework is really, really weird, and of course it's probably much more appropriate to put it either in a continuous time framework or at least some multiple periods, right, in order to allow for different effects. However, I don't really know in which direction it would go. Basically how information or the possibility of information in that setting then would, again, qualitatively affect the decisions today. Because of course you could more frequently revise your climate policy, and that might be good. Clearly, the value of information, at least in the expected utility framework, is positive, so that's always a nice thing to do. But since I think the crucial thing is then how to really model the irreversibility of abatement options. So basically, if we invest into certain power plants now, it's not just a one-period investment, but basically we really commit to a certain path, at least for the next 30 years. And I think then it would be a crucial question of how this irreversibility in terms of investment into abatement options is linked with its irreversibility in terms of building up a stock. And I'm not sure if really then the going from a two-period model to a multiple-period model actually would qualitatively change the results. So I think would be an open question, so I don't know about it.
A question for Min about you don't think that your outcomes result derive from the assumption of independence between the judgment of the experts? Because if you introduce correlation on dependence, you don't have a simple solution. You have to take in account this effect.
I don't assume that they are independent. So I assume that within each group they share data. They may share some data, but that across groups there are indeed independent. So actually there's a version of the rule that I use across the groups that doesn't make this assumption. But it wasn't published by the time I did these simulations. So you have also a pointy union operator.
Then I think we should have a little break for 15 minutes, and then we come back to the final discussion here, panel discussion. Thank you.